Welcome, everybody, to the Friday noon talk of the Medical Physics Unit at McGill. My name is Yves Levesque. I'm a professor here in the Medical Physics Unit, and I am happy to welcome a colleague of mine from the MGH MRI research platform, so at the Montreal General Hospital. William Mathieu, Dr. William Mathieu, is a recent graduate of McGill University in electrical engineering, where he has done some very interesting work on radio frequency receive coil design for magnetic resonance imaging, and this is what he's going to talk to us about today. We also know each other, as I mentioned, from the research platform, where we work together on a variety of hardware projects and support the many users who are present at the facility and acquire the data there. I'm actually quite proud and impressed to say that William has been an amazing engineer at that platform. He's not going to talk to us about it today, but I want to mention that he's managed to well, I guess reverse engineer a Trio 3T system, the parts of which we had scavenged from another site, who were giving up their system and moving on to another MRI system. And what we're doing with that is using it to drive novel gradient and shimming hardware, RF coil design. And so we have this sort of Franken scanner where we have a modern Prisma scanner with a magnet sitting in the imaging facility, which is what most of our users have. But we also have a separate Trio console, which is an older design, but that has all the hardware and amplifiers and everything we need to drive these custom gradient coils. It's been a project now of many years to resurrect this scanner, and we've just recently managed to bring the AC88 coil, which is was a landmark design from Siemens for gradient coils for high power gradient performance, and it's quite impressive that William, I think, I don't want to say single-handedly, but almost single-handedly managed to get the system up and running for us with help from Siemens and help from other sites. And he's done all of this while doing his PhD. So I would say one of the strong MR engineers we have here at McGill. Hope he'll stick around for a while. But today he's going to talk to you, as I've mentioned, about his work in receive coil design. So I hope I've given you enough laurels and made you feel a bit shy about everything I've just said, but you could be proud of the work you've achieved already. And I'm looking forward to hearing about your research project. So, William.
Thanks. Yeah, thanks for that. I don't know what to say. That's great. Okay. Well, I do have a few slides about that, so I might get to that as well. But the main thing that I'm going to talk about is the Equitable coil, so my PhD thesis. And so this is like a high channel count coil, and obviously I'll get into that. I had some help from a few people. Can everyone see I just want to make sure everyone can see my mouse or. Yeah, is that okay?
Laser, if you like.
Yeah.
Might be able to. Oh, it looks like. Well, don't know.
This thing?
To the left.
This thing?
No, left.
Left. Other left. Right.
There.
Yeah. Okay, there we go. Okay, cool. All right. Okay. Yeah. So I've worked with some people here. So I think I don't know if you know Jorge. Yeah. Okay. Yeah. And Evan. I'm not sure if. Oh, sorry. I mean. Oh, that's embarrassing. Okay, well, Jorge is there. And Evan as well, which I don't see now, looking like very carefully. Okay.
He's otherwise up.
That's okay. Yeah, it's all good. And so yeah, I kind of went through that, Eve just went through kind of all of that. So I'm starting a postdoc as well. So I'm just gonna kind of stick around forever probably. And yeah, I got it sort of, I crossed the stage yesterday, so that was fun. So these are kind of my two supervisors that have been supporting me this whole time. So Melissa's from Double E for electrical engineering, and Reza is my sort of longtime sort of day-to-day supervisor from ophthalmology. I went to him first about coils about a decade ago, and then I roped Melissa into that as well. And then a few years, well, 2018, 19, then Eve popped into the picture. He's been a great mentor actually through sort of professional and also some personal things. So that's been great. I have a great support system. And I think that's probably why I've been able to do a lot of cool things. Okay, so my research, yeah, Eve touched on that very quickly. So I have, I do a lot of coils, some simulation that we're trying to get better at. And I do some insert stuff, also some TMS fMRI, which was my master's project, and I have a few more slides of that. Okay, so anyways, back to the main topic. So this is the equitable coil. So basically it all started with kind of this years ago. This is Keel and colleagues, and him and his team did different pediatric coils for different age groups. So you have neonate here all the way up to 7 years old. And he's comparing this to like the normal average adult coil, which is pretty big and doesn't change shape. And so this is where we really started, and we saw that, okay, well, depending on the size of your head, basically, or this some evidence like the size of your head can actually impact your, you know, the quality of signal. So I went off and I built a few anthropomorphic heads, and this is like a 50th percentile, 5th percentile, and did some axial scans, and these are SNR images, and you'll see a lot of these throughout the talk. And let's say I just decide to window it to 40. So everywhere here inside this like darkened area is an SNR of at least 40. And you can immediately see that the smaller head here is kind of missing out. And so they could potentially have issues with, you know, the quality of their medical care. So based on that, kind of the whole goal here is let's offer the highest SNR possible, regardless of the patient's head shape. So I'm going to go through a lot of methods, but the elements are sort of on these semi-flexible plates. The plates are inspired by the cranial bone. So here I have like a photo from Gray's Anatomy, which is fun. A recent version anyways, and it has to be adjustable, different heads. We like to kind of target cortical gray matter because the elements are very small, get most of the adult population. And also we want it to be mechanically stable and safe. And this is a big deal because you want your researchers, your technicians to be able to repeat measurements easily. It should be sort of relatively easy to use as well. Okay, so before I go on, I just want to touch on two things about coils. So this is proximity and coverage. So here I have a coil on its side. So you're just seeing like the side view. And you see like if I move this closer, and this is a simulation, if I move it closer, you can see the field inside the volume gets much stronger, right? And another key point, which was developed by, excuse me, Romer and colleagues, is that you can do arrays. So here we have like a really big loop, again, kind of on its side. You can see the SNR is pretty good, but it's sort of distributed. But what you can do is you can take a small loop and it'll give you really good SNR, but over a really small area. And so by making the design more complex and adding more elements, you can create an array. And this is something that's done in antennas a lot, but this is sort of was adapted by Romer, and you can get really good SNR over a large area. Okay, so the main thesis idea is that, so these smaller elements, they provide really the higher SNR, but they have really small FOVs. And maybe we could solve this by placing them closer. Maybe this could be achieved with an adjustable design. And maybe the adjustable design could also provide it for different heads as well. or regardless of head shape. So there's I'm going to do a few slides here about background first. So here's this is Wiggins and colleagues. They did the 96 channel at 3 Tesla in 2009. And this is kind of a rigid bell-shaped former that they're putting everything on. Keel did a really good 64 channel with sort of a removable top. Then there was 128 also at 3 Tesla, but for the torso and cardiac. And then recently there's been one by Gruber, and this is a 128 cortical coil for 70, and there's also one for 10.4. There's also some really good, like, these are all rigid designs, so they can't really conform to different head sizes. There's a whole bunch of background when it comes to flexible designs is really popular. So this is a wearable elastomer. So this is like an elastic band that's conductive, and you can just kind of stretch it and bend it around whatever you like. And you can see that it takes kind of a hit, a little bit of a hit when it comes to comparing it to the copper. I know this is kind of small, but the blue line is kind of like your copper case, whereas when you do an elastic design, then it starts to kind of suffer in terms of SNR, but still pretty good. There's also these screen printed coils at 3T. So again, the control or the rigid or copper is, you know, the best overall. And then when you start to go to these screen printed coils, then you have sort of tiny losses here. And this is actually a doll with not like a real baby with the coil wrapped around it. So they're showing how flexible it is. This is a size-adaptable 13 channel. So this is really close to my design, and they have these pneumatic plates that move around, but they're not quite, they're not really head shape plates. They're just sort of like if you took a bell and you cut it up, and it's kind of a lower density. So only 13 channels. And so, but this is really like the closest thing to my work, and this is where I wanted to build on. So I wanted to put more elements, and we call that like a denser, improving or kind of increasing the density of the elements. This is also another one that I like to show because it has like rigid and flexible parts to it. And this is really good because a rigid coil is very stable. It provides really good SNR, like I was saying up here. But like I said, it doesn't conform very well. Okay, so I'll go into the methods now. So this is the start and where it all started with the mechanical design. We have this sort of average head from some data. And then we decided, okay, let's look at the cranial bones because this is a really great way that, this is like an efficient way that that nature has found to sort of like deal with the demands of DNA and variation in all of our brains. So we're kind of like inspiring from this. There's you know, some talk about, okay, well, maybe the plate or most of the plate is pretty fixed, and then it grows around the borders to account for different variation or to deal with different variation. So based on that, came up with these sets of plates, and these guys came from many iterations. So over here, I did started with that average shape and then started to tile it with these hexagons. And looking at that, you can kind of start to break up those hexagons into the plates. And then you can look at here, say, okay, well, these two elements could actually be on the frontal plate. So you move the boundary a little bit, and through a slow process, I came up with, you know, how to increase the number of elements and still sort of preserve this plate idea or this cranial shaped idea. And that's where these final plates came from. Okay, just want to look at so the other part is the mechanical design of the support structure. So there's a whole bunch of kind of strange ideas at the beginning. This was like a design where it can open. This is a deviation where I was working on maybe putting all the electronics in these sort of boxes that can move around. And then finally, because of the stability of this and also the number of electronics, we just decided to go towards like a big box that you can put everything in. And you can control the plates from the outside using these sort of sticks or pistons. So the piston design is like you turn this knob and then you can move the plate around. So that was like a really early attempt at this. And then, like I said, we have those towers where you have a whole bunch of adjustability and you can see some hinges there and things you can move around. And then finally, this was closer to the kind of gear shift idea. So it's like in a car where you can move the stick in the car and then it moves the gears in your transmission. So it's sort of kind of like that. This is really complex though, and it gives you way too many degrees of freedom. So kind of moved on from this, and sometimes a simpler design is better. So I moved on to just these pneumatic pistons that just move in and out basically. And I had a lot of trouble with actually doing this because there's no non-magnetic pistons that you can just buy off the shelf. So I used a whole bunch of plumbing parts. I think this part's used for like irrigating your lawn from the hardware store, and put all of these guys together and 3D printed this sort of piston plunger thing. And that was sort of okay. It wasn't super stable. So I moved on to these uh, threaded pistons. So basically there's a non-magnetic nylon screw in here and you move the green dial and you can move the whole, the blue and the yellow plate in and out. And I put that on all of the anterior plates in the design. So it looks a little bit kind of scary. And that's probably something we're working on as we go forward. Okay, so I'll go quickly through the electrical stuff because there's kind of a lot of it, but you can see here that this is just a very early attempt at putting these tiny elements, usually they're much larger, putting these tiny elements together. And you can see that the footprint of these little boards that have all the capacitors and sort of things that you need for tuning and matching, they take up a lot of room on the plate itself. And this is kind of an exaggeration of that, where you have, a lot of space for someone to solder and stuff, and it's easy to work with, but takes up a ton of room on the surface. So we decided to go towards these vertical boards and went through many iterations. I had some help from a master's student for this. And then I finally came up with these, the vertical boards that have two elements on each side. So two channels. So that reduces like a lot of room. You just have this tiny footprint here that's on the board, and you can then put the density of elements and channels that you want to go to that 104 channel number or higher if you want. So here's the circuit, and I'm not going to go through that, but if you have questions, let me know. I put two of the red part on this board, like I said, and I also have these tiny boards that I made for the capacitor, the tuning capacitor, and then this is where they ended up on the plate itself. So you can see there's actually quite a lot of room on the surface now to pack those elements in. The other thing is I put the elements on the inside surface. So usually you have like a box or you have your bell shape and then the elements on the outside of the bell shape. Here I put them on the inside. These are insulated wires, so you're not actually going to shock the participant or patient. And I also put some other layers of protection on top of that. But this approach made it so you can get the elements which are quite small, have small FOVs, like I was saying at the beginning, And so, you know, we really have to get every millimeter that we can. I designed some boards that kind of mate with the Siemens amplifiers. And here's the whole chain. So I made these boards as well. And this is my stuff basically. And then it kind of interfaces with the Siemens or the proprietary stuff. So I know there's a little bit of details, but I thought I would bring it up. And then there were a bunch of other parts. So these green and brown boards are from Siemens. So I had to design all of this mechanical stuff so that they can actually plug into the right spots, as well as some extension cables. And yeah, various other things that allowed for integration. Okay, so now for the actual coil itself. So here's just before I put it all together. This was one of the first times that I actually put everything in the same box. So it's a little bit messy. And this is months late or kind of a year later where I put one of those anthropomorphic phantoms in there. And then here's a few other views where I'm using the sphere phantom. And also the whole thing on the table. Right, so the initial results here, I have some scans with my coil. So this is my coil and then a cortical and a sagittal scan. Comparing it to the product coil, so that's just a Siemens 64 channel. And if I take this row of voxels and I plot it over here, I start to see, so I plotted it over here, I won't go too fast here. And each one of these is a layer of the brain. So I'm kind of estimating where the signal would, or how high the SNR would be at different depths into the volume. So I have like a layer for scalp, for skull, for CSF, gray matter. Of course, there's like a whole bunch of other layers, but this is the sort of simplest. And you can see in at these depths here, you start to gain, we're kind of gaining over the product coil. Okay, and then this is some more data about the head phantoms. So I have I tested the small one and the medium or the average head, and did another plot just to show and compare. And again, we get like really nice gains at gray matter depths. So this is 3 in the smaller head and then 4 up to 4 times. This is average gray matter SNR, and I just averaged basically all of the yeah, I just took an average of all the voxels basically along that line. This is noise covariance matrix. I don't know if this is something that you guys kind of know about or not really. Okay, so it's okay. I don't have to explain this so much, but basically it says like how well all the elements are decoupled from each other and gives you some information about a few other things. And so I just put this in as a comparison. You usually want to show that your elements don't talk to each other too much, because then they actually you're losing something you could get for free. So 3% overall is quite good. And usually you have between 11 to 14% with a product coil. And depending on like the nature of the coil, you might just accept that it's a bit higher because you can actually image the thing that you had trouble with other coils. Okay, so then I scanned my head with my coil and compared it to, so this is 100 channels, comparing it to the product. And you can kind of see like it's quite nice in the periphery here. You get really high sort of SNR. I'm going from 0 to 50. I have a tiny problem here, which is still kind of something we need to work out. But if you do that comparison again with the line of voxels and you compare that, you see that again, there's really nice gains in gray matter. So this is still preliminary, and I wouldn't say that it's like publishable yet, but it's kind of showing us that we're on to something really good. So that's my head again here, and I also imaged a smaller head with the same coil, same conditions, and you see this person has again gains quite well. Like they actually do better in the coil with their smaller head, which is great. Here's some images of comparing just a 0.5 millimeter MP rage, and that's my coil here and the Siemens. Again, this is kind of preliminary, so I don't want to just jump on like, wow, look, but it's kind of showing us that we're like going in the right direction. And there's really nice white and gray matter contrast here compared to the product coil. So that's really good if you're doing like segmenting or you're trying to figure out cortical thickness or cortical volume. Okay, I also did some acceleration results. So this basically says, I don't know if this is something you're familiar with. Accelerated imaging, so iPad or Grappa, Sense. In this case, it's Sense. So these are results to show how good the coil is at doing accelerated imaging. So it might be kind of difficult to, if you're not a coil person, but essentially the more red you have in each one of these, the better you are at acceleration. So here I'm doing a factor of 2, 3, 4, up to 8. And I've put this sort of max G factor. So all in all, what I'm saying is that, you know, how much does the SNR actually decrease as I accelerate the image? And so my coil has been able to show that it does actually quite well compared to the Siemens coil. And I also plotted that here. I know this is like a lot of data thrown at you at once. But it's kind of showing that like this is doing the, you know, it's just kind of something that I didn't expect because we wanted to do really high SNR in the gray matter for different heads, but also it's showing that it can do acceleration really well. So yeah, I have a few. I'll skip over that one. I also did that again with my head and versus the Siemens coil. And so again, like it's very good 1/G factor. We see a lot of red there comparing this to the same condition in each acceleration to the product coil. So as you go higher with acceleration, you do, you know, not just AP, but left, right, you see that like a coil like mine actually does very well here. Okay, so with this, I don't know why I figured I would just throw this in here because I did a few journal articles, some conference papers, and also some posters and talks. The most recent being at ISMRM, right here. And I have, I'm not sure how much time I have here. Plenty of time? Okay. So I have kind of some results from each of these papers that I can go through. And it's not as interesting as. It's fine.
C, niveau F1 à l'urgence, chambre 56. Attention, code white
Yeah, I'm just gonna take
block C, Charlie, level S1, emergency, room 56.
Okay. So for these papers, I have a variety of results. So I'm going to talk about 3 of the sort of body or 3 of the well, in each paper, there's like some results. So I'm going to go through 3 of those basically. So first I did a long time ago, building up to the results that I just showed, bending studies. So I took one of the plates and I bent it around different shapes and simulated it to kind of show how well the coil is behaving and if there's any actual issues when you bend it around different objects and shapes. Sorry, it's laggy a little bit. I did that so in simulation, and then I did that on inside the scanner. So I wrapped this coil around each one of these and I compared that to the Siemens coil. So just the posterior. So this is 18 channels versus 20 channels. Sorry, 40 channels of the Siemens coil. And here are the results from those tests. And I also included the plots, the line plots that we like a lot. The coil people like to see a lot. So yeah. So anyways, I'm plotting the column of voxels here and each one of these and comparing. And again, gray matter is doing quite well, or the adjustable coil does quite well compared to the product coil. That's just kind of makes it a little bit bigger, easier to see. I also did plate separation, so you saw that they're plates and they move, you know, obviously for larger heads, they move apart and then you can kind of maybe guess that there would be some loss in signal in the gap between the plates. So I wanted to actually characterize that, and I ran a test with different separations of just the two frontal plates. And I can see here, so I'm taking the voxels that are right underneath each of the plates to show how bad or how much of a decrease we get. And so, you know, it's kind of up to interpretation, but you can see that you get at least 75 units, or these are arbitrary units, for, you know, the 10 to 20 millimeter separation. So this is normal head sizes. And then this is a good example here at 27 of when you're actually going further than you need to. So 27 is bigger than any head you would ever encounter. And so we're showing that the design starts to not be able to service that case, but that's totally fine because it wouldn't exist anyways. And I'm showing also the slices that were taken axially here. And again, it's got pretty good coverage and uniformity. I also did some stuff, these bowing elements. So I had a paper about that. And these are elements that could potentially bridge the gaps between the plates. So that's what I'm showing here in this diagram with the blue, sorry. And these elements are basically like, they could either be semi-rigid, semi-flexible. And here I'm showing the case of potentially in the future using two very flexible elements that can, you know, if you move the two semi-rigid plates together, those two elements would move up and out of the way to accommodate a smaller head. And then if you need more coverage for a larger head, then this could potentially solve that problem. So I did a test with this little setup with just two elements, and I got some nice results that show that compared to a conventional coil. So sorry, I'll slow down a little bit. I have just two wire coils that I'm moving over one another, and I'm comparing that to the two coils here that are in red that can kind of bend together and up. And I'm just basically doing a study of how well those two compare. And so here at the top row, I have just those bowing elements. And compared to just the control, we're getting better, you know, more sustained SNR as you push them together. So simple, but pretty effective solution for this. Okay. So that's it for the thesis work. I have a few slides that I'll go over and about the other things that I do that might be interesting. But here we've been able to show that we can at least triple SNR at cortical depths. We have acceleration performance that's like 2 orders better. So if you accelerated at, let's say, 2 times with the regular coil, that's just as good as the performance of my coil if you did 4 times. And yeah, we showed that it can properly actually adjust to different heads and get pretty good SNR gains. And this is overall supporting more equitable imaging. So anybody you send to me, I could probably promise that they will gain from this coil regardless of the shape of their head. Okay, so I have these other slides, there's like 4 or 5. So I work part-time as a research assistant or a sort of MR hardware engineer at the research platform. So I don't know how much Eve has told you about his other work. So this is like a subscription-based plan. So you this is not, I'm not trying to like plug this or anything or like advertise. This is more just for fun. It's like we have researchers that come and the students can basically use the scanner for a certain number of hours each week, depending on like the plan that they have. So we train up the students to actually operate the scanner and run the studies. And of course, this is limited to just research. We can't use it for any kind of clinical things. So there, I have these other projects that are running. So I have a shim insert. So this is gives you higher order shims. Usually your scanner might do 0th order or 1st order. This has 28 channels in it, and it can do, I think, up to 4th or 5th order. And we have a transceiver coil. We also have this strange design where we put the patient in the other side, or the participant in this case, through the other side of the scanner. So I'm putting all the equipment and the coil on the actual bed. And then we built this blue bed that you can lie on and push the patient or participant in, and they meet in the middle in ISO center, and you can image them that way. So this is like a nice way of handling equipment that we've come up with. And we also have a few I have a picture of the AC88 gradient insert. So basically somebody would be brave enough to climb in this with their head, and this replaces the gradients of the actual scanner. So you can do faster changing, like faster slew rates or stronger gradients, but only over like a small area like your head. Okay, and I also mentioned we've been trying to do interleave TMS fMRI. So here's a postdoc from a few years ago that we strapped in, and we're using the Siemens coil here, which is just that flex coil. I don't know if you're familiar with it. And we wrap that around his head, and we also have this TMS. So this is transcranial magnetic stimulation, and it's a very strong, very short magnetic pulse that can actually depolarize neurons in your head. And we kind of want to see what happens whenever we do this sort of pulsing. And so this is the stimulator itself on that arm, and in this picture you don't see it because it's under his head. But one of the big issues is that the coils are super bulky. So a thing that I'm trying to work on is making them very thin. And so you can put the stimulator even closer. And then finally, we have a few up and coming small animal gradients and other head gradients that exist but aren't working yet, but could kind of provide some interesting studies. Yeah, and that's it. Yep, that's all.
Thank you very much, William. We'll open the floor and the online presence for questions.
Yep.
Jorge, go ahead.
First of all, really interesting work.
Thanks.
Thank you so much for sharing. I was wondering, you did a great job presenting how the work that you did
Yeah,
to adapt your code to the proprietary hardware of things.
yeah.
How was the experience in the software side? How did you live for the Siemens platform to get well, like to play well with your code?
So you have to basically it's like a customer coil, so you have to write your own coil files for it, and also try to interface with their strange electronics, which they don't always give you all the details. They kind of say, okay, well, the plug's here, but so just like yeah, just sort of figure it out. So it was a little bit tough actually on the software side. Yeah, but I think the guidance was pretty good overall. Yeah. I don't know if that answers your question or if you mean, yeah, okay.
Then technical question, when it comes to size adaptable coils,
Yeah,
I guess that changing the size will also affect the coupling of your coil elements. And will potentially affect a little bit the performance when it comes to parallel imaging.
yeah.
Is this a concern in your coil? Will the effect will substantial depending on the size?
Yeah, so that's true. So the smaller coils, it's kind of tough because you can do the overlap of the neighbors and you can that kind of fixes that problem. But because they're so small, the next neighbor over, I have actually a slide for this because I get this question. Here. Yeah, so this is really easy to decouple. Well, not really easy. It's, you try your best. But of course you can't actually use this critical overlap for the next nearest neighbors. So you do usually preamplifier decoupling. So the way the like loops interact is is like through mutual inductance. And that's governed by the amount of current that's going through each side, basically, of the two loops. So what you want to do is you basically use preamplifier decoupling to minimize the current as much as possible to try to minimize that. And that's kind of the only thing you can do to work around this problem. Yeah. So like it's very much on the edge because larger coils, it's easier to do this. But then smaller, yeah, it gets harder and harder, and then you sort of get to a point where you might actually you can't do anything about it. Yeah. Yeah, no problem.
There's a question online from
Oh,
Mirta.
Yes, great talk. Thank you so much. So interesting. So from a non-MR expert, I hope that's okay.
Yeah.
So what's the origin of this effect that you see such a, stronger SNR for smaller heads with your, I believe it's a 100 channel coil compared to the commercial one. And then I noticed that at one of your slices, your SNR was asymmetric. I
Yeah,
don't know if I remember that correctly.
Yeah.
But yeah, what's going on with
Yeah.
that? I would think it should be symmetric, but
yeah,
Yeah.
no, that's right. Yeah, this is actually simply just because I'm having trouble with one of the elements, or there's something to do with an element here that's giving me some trouble. So this is still all kind of in development. And so what you're actually seeing is that this guy is actually kind of killing some of the signal in the area. And that's why you're getting this this sort of slightly uneven effect. So yeah, basically this is kind of a work in progress in some ways, and this is one part that's still not quite perfect. I
great.
don't
And
know.
how about the smaller head be having such great response?
Yeah, yeah, that's true. So this is trying to be about equity, and so when the smaller head gets like even better, then it's like, okay, then maybe the average head misses out. But I think the point that I'm trying to go, or what I'm trying to make is like, if the improvement is still better than the Siemens by, a few, orders or a few times, then it's like everybody's sort of gaining from this instead of just somebody who makes 100 channel that's really good at just my head size, or like a big head or something like that. Yeah. So
So
this is,
that potentially for pediatric cases would be even better.
yeah, exactly. Yeah.
Thank you.
Yeah, thanks.
What's the minimum head size your coil can reach down to? So in other words, at what point do your plates touch and can you stop moving inwards?
That's a good question. We were kind of there with the 5th%. I was sort of already there.
5th percentile of
Yeah, so
adult head size?
of adult heads, yeah.
Okay.
Yeah. And it's really hard to find this 5th% because there's not a lot of data out there about people's head shapes and sizes. There's a few sort of ballpark
And
estimates.
how does that compare? Did you compare that to say like pre-adolescent head size or?
No, I didn't actually, but
I guess it, given Mirta's comment about
Yeah.
working towards pediatrics, I guess there's sort of a good amount of head size change in the first 12, 15 years of life.
Yeah.
At which point I think probably flattens out a bit. Yeah.
I did notice that there was some data about like kids' head sizes because often we track development, I guess, of
Yeah.
the head size. And yeah, around the mid-teens, it starts to be very
Almost adult.
stable, like you say, yeah, almost adult size. That is what I remember at least, but
Okay.
yeah, I wonder how close the 5th is to
That.
or to, yeah.
I pick up a.
Yeah. Oh,
Peter, did you have a question?
I have a more ignorant question. Is it a problem?
There are
that
no
crest
such
marks are
things.
Not uniform. Is that ever an issue in image analysis or whatever? Because obviously when you show the pictures, it looks
Yeah.
better at the.
Yeah, yeah.
Surface, and as you get deeper into the brain, it gets worse, but you're interested in what's.
yeah, most.
Is that ever uniformity ever something that's desirable? That's
Yeah, I think, yeah, no, it definitely is, and like you probably noticed, you know. Yeah, you probably noticed here that there are still some of these gaps. Yeah, that would be interesting to study, like if the gap is still, like this point is still better than this point here on the product coil. In which case, in terms of SNR, it'll say, that point will be more accurate at measurement. So it's okay that it's not like exactly uniform in terms of SNR, but it just says that maybe you have like a certain confidence in your measurement in each of the points, and it's better in these sort of higher region, those spots, yeah.
But I think along these lines, I think it's worth you maybe mentioning why it's okay. Like I think what Peter's pointing out is not just the uniformity around the edge of the brain, but
Yeah.
also the fact that you've got non-uniformity edge
Yeah.
relative to center. And maybe you
Yeah.
want to comment on if that matters, in what cases that's interesting, in
Yeah.
what cases that's not.
Well, yeah, I think that if you had to image like the hippocampus, this would probably not be the coil. Like if you were interested in really like gray matter, or even though, yeah, the cortex folds in at some points, especially the back here, in the visual area, you'll have gray matter deeper in the brain. So yeah, in that case, it's probably not a better coil, Yeah. So there's a few limitations. It's kind of, you don't get anything for free. You have to take it from somewhere else.
Maybe,
Yeah.
Small question. I don't know if I saw the pictures wrong, but I think compared to the scenes coils, your coil is more enclosed to mine, right? Like there's less of a exposed, like would it cause the patient to more claustrophobic?
Yeah, for sure. Yeah, I think that's probably one of the parts that we could work on because, yeah, with my head in there, I know everything about this coil, so it doesn't really stress me out. But Reza, my supervisor, is a little bit scared of it. So that's, yeah. So that's probably that's definitely something that we're working on as somewhere to improve. Not sure exactly how to do it. Yeah. Yeah, that's definitely a big issue.
Maybe I wanted to ask in that same line of thought, since the gold nature of the coil, which ear protection can you use inside the coil for the future?
Yeah, for this I just used it actually pushes against your ear quite well, so it kind of blocks a lot of the noise. I had just those earplugs in with the plates. It was actually pretty good. Yeah. I also had a little neoprene diving cap on there as an extra layer just in case. So I'm not showing any of those pictures because we all look ridiculous.
Into
Peter,
IP
go ahead.
protection, commercialization.
Yeah.
Invented something new, to be cool, and considering patenting.
Yeah, actually, we did a, what's it called, preliminary or like provisional, that's it, yeah. So we have that going at the moment. So we have just under a year, yeah.
We still have some time. I'm gonna needle you a little bit.
Yeah,
In that so you made some SNR and acceleration factors, so R value comparisons and G factor math comparisons. So
yeah,
those, I don't mean to throw those terms around too much. I mean, I do explain them a little bit in our coursework, but they basically have to do with overall SNR efficiency of the coil. So how much
Yeah.
how much SNR are you getting for a given setup and comparing them side by side with a commercial coil? So I don't know if you want to
Yeah.
flip to like a slide where you're showing G factor maps, we could talk
Yeah,
about G factor. And so that, you know, as you explained in the talk very nicely, having a small G factor or a large G factor, a small 1/G factor is what's interesting. No, it's not. No, it's the opposite. 1/G factor has to be close to 1.
Yeah.
So a G factor close to 1.
yeah.
Right.
So you're minimizing, so these numbers here are your max G factor.
Yeah.
So you're trying to minimize those.
You're trying to make
Yeah.
those numbers small.
And then,
So
yeah.
the red map is a good thing.
Is better, yeah,
And as you show in these images, what happens is the G factor is acceleration dependent. So that's a sort of well-known effect.
yeah,
It could be calculated and it can be measured,
Yeah.
as you've shown here. And obviously you're getting nice acceleration performance from this new design coil compared to the commercially available. And so you're reaching higher acceleration factors for equivalent degradation of SNR.
Yeah.
In other words, you can go faster and not lose as much SNR along the way.
yeah, yeah.
But I wonder, did you take the time to think about you've done some of these comparisons in different head size maps? I can't remember if you had factors for different head sizes yet.
I do have the data, I just
Okay,
don't
you can
have,
show it
yeah.
today. So I guess I was wondering if you had, in terms of comparing apples to apples.
Yeah.
You've done two things, right? You've increased proximity of the coil element to the head,
Yeah,
and you've increased the channel count.
yeah,
Now, great, those go together, but how much of this G factor gain is from the higher channel count versus G factor gain from proximity?
oh,
Do you think, have you thought about that, whether one matters or not, or whether one enables the other? Because, you know, could Siemens have built a rigid coil with 104 channels and gotten
yeah.
very close to what you're getting?
I don't think so. That's a good question.
Yeah,
I don't, because I think that, you know, the fact is that in parallel imaging, like over here, yeah, so like this is like SNR in parallel imaging, right? So that, so I think that, you know, whatever you start off as up here, the higher you can get that, the better. So I think that's like, you do need both those things, I would say. So the channel count and the proximity squeeze as much SNR out of it as possible.
Okay, so you're suggesting then that the starting SNR, which is the numerator on the right
Yeah.
side of that equation.
Yeah,
That already accounts for channel count
Yeah.
differences, and that the G factor would be. Or no, so the SNR would actually already account for channel count plus proximity.
exactly.
And that the G factor would be
You would count,
acceleration related and therefore channel count
yeah,
related.
yeah,
Okay. Yeah, because I mean, it is an interesting question of where did you make the most gain, right?
that's true. Like what out of the two things actually caused the most gain? Yeah,
Because if you go back to the slide you just put before with the heads, you know,
Oh.
I have to say I've seen
this,
no, with the G factor maps.
oh, sorry, yeah, in that, yeah,
you know, achieving a G factor of very close to 1 with 3x3 acceleration.
Yeah.
Is very impressive. Like that's a really high acceleration. Now,
Yeah.
you're gonna take a 1 over square root R loss inevitably,
Yeah,
which is
yeah.
not pictured here.
No,
It's
exactly, yeah.
only the G factor, but it
Yeah.
does talk about uniformity. And then I guess back at your defense, I don't know if I think the question was asked about how the performance was in the center, because this comes back to Peter's question, and maybe that's where we'll wrap up. The performance in the center of the coil, and this was a question that goes back to the earliest designs of multi-channel coils,
Yeah,
is how well they're performing on the periphery. They do much better on the periphery, but do they maintain performance at the center of the
yeah,
coil?
yeah,
And what it looks like is you're taking a little bit of a hit. at the
yeah,
center
for sure,
In
yeah,
terms of performance. So in
Yeah.
terms of whole brain imaging, there might still be a bit
yeah,
of work or distance to cover to get back, I guess,
back that part, yeah.
to that.
Yeah.
part.
And that might be where we just say, okay, this is for,
The specialized.
this is specialized coil.
It's not a big difference. There's not a big loss to go.
Yeah, yeah.
Okay. All right. If that takes care of all the questions, I'd like to invite you to thank our speaker again. Thank you very much, William. Thanks. Getting your work with us. Thanks everybody for attending, and have a good rest of day.
Yeah.
Right.